Second one we are going to discuss is about to derive a relation between various physical quantity. And learning this is, I think, the most important thing of dimensional analysis, because it helps out a lot if you know how to use it. So let's take an example. So let us derive time period of simple pendulum. So to derive the time period of simple pendulum, we have to suppose something. Suppose meaning we have to consider some things. So suppose the time period of simple pendulum depends on. So you might ask, how do you know what it depends on? Well, you have to take a guess. In most of the cases, you see the behavior of the pendulum and you guess. So if you guess correctly, it works. If you guess incorrectly, it sometimes works. Okay, it works sometimes. So it depends upon length, which I will represent by L, length of string, so it's length. Then next is acceleration due to gravity, which will be small g, and mass, m as. Okay, so think about it. If I have a simple pendulum, if you don't know what a simple pendulum looks like, so let me draw it. Simple figure. So a simple pendulum is basically a long rope from a rigid support with a heavy mass in the bottom. So this is a heavy mass. Um, so this mass, let's put it with another color. This color is great. So this is a simple pendulum. And it moves, it swings. We will learn about simple pendulums in one of the chapters that I will teach you later on. So as you can see, it moves, and it will move till some point, then come back and move some more and come back, and it will vibrate. So think about it. If we have a longer string, it will take if you have a longer string, it will go much more farther, or much more the range will be more. So think about it. If the pendulum length was not this, and suppose it was over here, it would go to, suppose, here, where this one would only go for here. We don't know, we're just assuming that. So next one you would think is, if the gravity is stronger, the bob will be pulled more when it's not in the equilibrium position. So if it's over here, the gravity will pull it more strongly. If the gravity was stronger, then it would bring it to the center pretty quickly. And finally, if we think about the bob, this is called the bob. If the mass of the bob was increased, it would also have some effect. It might have or it might not have. We are just considering that it has. So now, since it depends on this factor, we are considering that it depends on this factor. We don't know how it depends. So let's say the time period, I'm going to suppose it as t. I should have written t over here. So t is directly proportional. So it looks like alpha, but it's different, okay? It is directly proportional symbol. So it is directly proportional to length. But how? To the power a. So a can be any number which is to be found, okay? So we can write t is directly proportional to z b. And finally, should I write it over here or down? Let's write it in the next page. Why not? So t is directly proportional to m to the power c. So let's give these equations 1 to 3 number. So this will be equation 1, this will be equation 2, not equation, I mean relation, relation 3. So where a, b and c are constant to be found, or determined. So now what do we do? So what do we do is we combine all of the three equations. So combining equation 1, 2 and 3, we will get t is directly proportional to L to the power a, g to the power b, and m to the power c. So to remove the proportionality sign, we will have to have a constant. Let's suppose the constant is k. You can write any alphabet, but c and k are generally written. So k, L to the power a, g to the power b, m to the power c, where k is proportionality constant. So now let's find the dimension of the LHS and RHS to find the powers of A, B, and C. So here, dimension of t, which was time period, so it will be like this, right? The next one, the dimension of length of the string L will be L, right? Similarly, the dimension of acceleration due to gravity small g will be Lt minus 2. Why must it be Lt minus 2? Because acceleration due to gravity is a acceleration, so it will have the dimension as the same as of that of acceleration. So now dimension of m, which is the mass of the bob, which is m, and here k is dimensionless quantity. So now we found that it is a dimensionless quantity. How we are saying that it is a dimensional quantity? Because we are considering that this is a dimensional quantity right now, because we only hope that it depends on the above three factors, which means that this final factor k will be dimensionless. It just makes our calculation way easier to understand and to do. So if there is a dimension, there is a quantity that has a dimension and is a constant, it will give us a little bit of trouble when doing it bidimensionally. So now also this equation, let's call this equation 4. It will make it easier because I will have to reference this. So right now, then equation 4 becomes, so equating them bidimensionally, we can write the dimension of t will equal the dimension of k, L to the power a, g to the power b, m to the power c. Since if they are correct physically, then it should be correct dimensionally as well. So let's write the dimension of each of them here: m0, L0, t. So k does not have a dimension, no need to write that. L has a dimension of L, which is raised to the power of a. G has a dimension of Lt minus 2 raised to the power of b. M has a dimension of m raised to the power of c. So m0, L0, t. So if you combine all of this, we will get m. So are there any other m? No. So it will be m to the power c only. So now let's look at L. Are there two L's? Yep. One has the power of a, one has the power of b. Finally, t, there is only one t, and it is raised to the power of minus 2, and it is again being raised to a power of b. So it will be minus 2b. Now we can equate the powers. Since the relation is physically correct, the powers must be equal. So let's write this in another page. Equating power of same base of same base on both sides, we will get that 0. Let's write it from the other way because it will be easier. We will find that c is equals to 0, which makes it our life much easier. And again, we have of length, so a plus b equals 0. And finally, for time, we have minus 2b equals 1. So let's call this equation number 5, 6 and 7. So now from equation 5 we know that c equals to 0, and from equation 7, so from equation 7 we find that b is equals to minus 1 by 2, so minus 1 half. So now from, so let's do it in another page. So again, from equation this one 6, from equation 6 we will have a plus b equals 0, and we know that b is minus 1 half, so a will be plus 1 half. Then equation 4, our original equation, becomes t is equals to k times l to the power a, so it will be 1 half, g to the power b, so it will be minus 1 half, and finally m to the power 0. So finally, writing this in a proper format or clearer format, we will get k times square root l by g. This will be our equation 8. So if you see right over here, you might notice something. You will notice that time period of a simple pendulum does not depend on the mass. Even though we consider that it depends upon mass, doing it bidimensionally, it will automatically tell you if it depends or does not depend. So it does not depend on mass. That's a crazy thing to find out. Don't you think about it? Like, you thought it dependent on mass. By just doing some calculation, you found that it does not. You don't even have to see the apparatus to know about it. You can just find it out by doing it dimensionally. So what about the value of k, you might be asking, because we just stated it as a arbitrary constant. Well, there's no other way around it to do it by experiment or do it by some other way. You can't find the dimension. You can find the dimension, but you can't find the value of the constant, which is a sad part of dimensional analysis. But still, think about it. You found how they relate. You found that it does not depend on mass. You also found how the length depends upon time, and how the acceleration due to gravity depends upon time period of a simple pendulum. That's crazy. So let's conclude it pretty quick. So experimentally, that's why experiments are also important, because everything can't be found theoretically, but the value of k that we find over here is actually derived. You can derive it, which I will show you in another chapter. I don't know which chapter, but there is a derivation where we derive the value of k. So experimentally, the value of k is found to be 2 pi. So you might have a question, how did pi come over here? So pi came because when a simple pendulum revolves, suppose when a simple pendulum revolves like this, it is revolving in an arc of a circle. Think about it. It's revolving in an arc of a circle because the length of the rod, so let's go back. So this length of the rod, it's not going to change, and when it's rotating, it's going to act as the radius, so it's going to actually make an arc. That's why pi comes up, because simple pendulum is also related to a circle. So whenever there is pi, there is always a circle involved somewhere. That's a key inside. It's not that useful for us, but it's a cool point. So the time period of simple pendulum is given by t is equals to 2 pi square root L by Z. And this is important formula, not right now, but it will be important someday. So that's it for today's video. In the next video, we are gonna do some questions about this, about this case. So that's it. Thank you.